Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. I'm Yvonne Stapp, and I welcome you to tonight's Contemporary Science program. It is a special honor to welcome Eric Chaisson of the Harvard-Smithsonian Center for Astrophysics. Dr. Chaisson is famous for his unified model of cosmic evolution, which he'll discuss tonight. This model shows the underlying connections between the epochs of the universe, from subatomic particles at the very beginning to the emergence of galaxies, stars, planets, life, and finally, human culture. All these stages are enabled by a few underlying principles that guide the evolution of the cosmos. Dr. Chaisson received his PhD from Harvard University in 1972. He's since been associated with the Harvard-Smithsonian Center for Astrophysics, Johns Hopkins University, the Space Telescope Science Institute in Baltimore, and Tufts University, where he was director of the Wright Center for the Science Education for 20 years. While at Tufts, he also taught in the Department of Physics. When he returned at last to the Harvard College Observatory, he developed a course on cosmic evolution. The famous course is an example of his deep commitment to science education. An illustration of that effort is his website construction, which we urge you to see, Cosmic Evolution from Big Bang to Humankind. You do not miss that. Eric Chaisson is a member of numerous science organizations and advisory committees. He's received many awards for both his research and his numerous books. His astronomy textbook, now it's an 8th edition, is the most widely used astronomy textbook about. But tonight we'll focus on his most recent books for general readers. The first, Cosmic Evolution, The Rise of Complexity in Nature, and the second, The Epic of Evolution, 7 Ages of the Cosmos. It is a very great pleasure to welcome Dr. Eric Chaisson. Welcome, sir.
Thank you, Yvonne.
And I'll start right in. Thank you. I'll start right in with asking, how did this very complex idea arise in your head? How did you come to that about the evolution of the whole cosmos?
Well, you know, when I was a student in Cambridge at Harvard, I tried to take a course that I realized I couldn't because it didn't exist. I had always wanted that bigger picture, that world view. I wanted to know more about how I fit into the bigger scheme of things. So then after many years of transitioning through the Harvard system as a student and a postdoc and becoming a young faculty member, I coerced a senior faculty member to come with me to create this course that I had always wanted to take as a student, so other students might take the course, but I never knew whether anyone would show an interest in it. Little did I know, within a few years, the science course we were teaching, Cosmic Evolution, was the largest science course on campus because students were voting with their feet.
Yeah,
they also wanted a world view.
Yes,
they wanted to know how they fit into the bigger picture.
But you were ahead of the game even while you were a student in that case, that this took shape that early.
My predecessor, though, at the Harvard Observatory was Carl Sagan.
Yeah.
And he was onto this,
yes,
and his predecessor at the Harvard Observatory was Harlow Shapley.
Yes.
And he was onto this for decades. So I'm just the latest in the line of people who have been onto this idea.
You put it together, I guess.
I'm trying to quantify it. I'm trying to bring numbers. I'm trying to bring mathematics. I'm trying to bring empirical understanding to the great ideas that these other predecessors had.
Right. Well, in your idea, you have a unifying theme. Can you explain it? As how did you put the whole universe together? 20 words or less there.
Well, you know, basically I look out the window and I wonder where everything came from, how it all came to be, in particular among the galaxies, stars, planets, life, and society that you mentioned, how complexity has risen over the course of time. And in particular, since I'm fundamentally a thermodynamicist, and I realize that the universe must be according to the second law, breaking down over the course of time, how is it that these islands of complexity have risen increasingly so? So that's what's driven me to understand, and understand quantitatively, how is it that islands of complexity can exist for long periods of time in an otherwise great sea of chaos and disorder.
And emerged in a kind of regular order as well. So,
well, that's the empirical finding. There was no a priori idea that the galaxies needed to precede the stars, or the stars needed to precede whatever. This is an empirically built, it's an observationally garnered idea, or sequence of ideas. And so we're finding that the story seems to move along a so-called arrow of time, from the simpler systems to the more complex systems, from the inorganic systems to the organic systems, perhaps from chaos in the old-fashioned Greek sense to order that we have all around us.
One of the interesting ideas that you have brought up in your books is the notion of chance and necessity, which fits right in with the whole thermodynamic idea.
A lot of people, of course, think that Darwin, with regard to biological evolution, thought that chance was trumping all the time. It was all chance. But he never really said that. In fact, it was a long conversation I had while hiking a mountain in Switzerland with Ernst Mayr, who eventually lived to age 100, but he would have been in his 80s at the time, who stressed upon me that if you really read carefully The Origin of Species, which hardly any biologist I know has read, actually, you realize that Darwin suggested that it was both a mixture of chance and determinism, or chance and natural selection. And so Ernst Mayr used to always say, really, in putting in another term, that it was a mixture of chance and non-random elimination. If a life form, or if a galaxy, or if any kind of a system that had some degree of complexity was suddenly changed by chance, it would then respond. It would either adapt or adjust, but it would do so according to fundamentally the laws of physics. And it's neither chance nor necessity. It's not randomness or determinism. It's unfortunately shades of gray all the way down in nature. It's a mixture of chance and necessity, which the great French biologist Jacques Monod in the 60s, in existentialist French, France at the time, said it would be a mixture of the both.
And they were talking particularly about biology, but you applied this idea to the cosmic evolution in general, and do you see it?
Well, for me, evolution is hardly more than another word, a fancy word for change. And again, if you look out the window, there's nothing permanent except change, as we often say. We sometimes attribute that to the Greek philosopher Heraclitus. I don't think he ever said that. He did say pantare in Greek, which means all flows, all fluxes, nothing stays the same. Those fragments exist. And it was probably the best observation anybody ever made 25 centuries ago.
Pretty good, yeah.
So we are trying to take this universal change, which I then call cosmic evolution, and apply it to not just life forms, but inanimate systems, indeed more advanced systems such as cultured systems, and see whether or not we can demonstrate a unity in evolution from the physical evolution through the biological evolution through cultural evolution. As a result, the kind of evolution we know best, which is neo-Darwinism, it becomes a small subset, albeit a very important one, in a much grander scheme of evolution writ large throughout the entire universe.
But so it was fairly self-evident to you to see this kind of underlying theme.
It's a strong word. Again, I'm an empirical materialist. I'm trained as an experimentalist. I demand that ideas be tested. So I might have had this idea, as others did too, but as I throw more and more data on the idea and test the idea with more and more observations and experiments and empirical findings, I find that the idea continues to hold up reasonably well. But it's not just an idea. It's an idea that's being quantified. It's an idea that's being tested.
Yeah.
Very important part of science and the scientific method, of course, in all of its confusion and bias and subjectivity, is that we must test those ideas.
Yeah, right. You have talked about complexity a great deal. Can you tell us this, because this evolves as well? Tell us about what you had in mind with complexity.
Well, there's simplicity and there's complexity. If you back me into the corner, put the bright lights on me, as we have here, and ask me what do I mean by complexity, I'd have to say something like a state of intricacy, complication, variety, or involvement among all the interconnected parts of a system. A system which is an assemblage of things, of components that are interacting independently, aside from and differentiated from their surrounding environment. So you have systems and you have environments. And in many ways, these systems, should there be, this is my hypothesis, a sufficiently optimum flow of energy through those systems can maintain their structural and functional integrity for a certain period of time, as long as they have a flow of energy through them. You and I maintain our structural integrity for about 70 years on average in the West. A galaxy or a star maintains its structural integrity for last billions of years. But basically all these systems seem to be growing in complexity, some faster than others, some more robustly than others, because they have a flow of energy through their systems and then a flow of wastes and the products into the environment.
Okay. Just one more thing on that. Can you say in general, when do you call it complex? When do you call a system complex?
That's why we're trying to develop a complexity metric. Nobody has developed that.
Okay, that's
Most of my colleagues in physics hang their hat on entropy, which is a very slippery term. We could talk about it forever and never understand it.
Especially with this kind of scale.
Yeah. Nor have I ever come across an entropy meter, like a thermometer, namely a thermometer. I don't know how to measure entropy. I don't know, even as a physicist, how to define it well. I certainly don't know how to utilize it in a mathematical setting as well as I'd like to. Among my biology friends, rather than energy, they would prefer in many ways to embrace information and information theory. I'm a simple physicist, kind of like a country doctor. I take something that I can understand, that I can define, that I can measure, that I have an intuitive feel for, and that's energy. It's an invention of the 19th century physicists. So some people in Cambridge will say, oh, it's an old-fashioned concept. But energy is a very powerful concept. Our whole civilization, our whole civilization just runs on energy, but so does a star. So does any life form in your backyard run on energy. Take away energy, or provide too much energy. That's they die. That's why there's an optimal range of not too little and not too much. It's kind of like watering a plant. Too little or too much. Is it just right amount of energy flow through these systems?
Okay, so they don't really have a real good handle on complexity. It's like a lot of these concepts, but that's at least there's an understanding that there is such a thing. We just don't know where to draw a line, perhaps.
But I can show you the lines that are drawn between and among, let's say, galaxies, stars, planets, life, and society in terms of the amount of energy flowing through those systems per unit time.
Okay.
And I can put a quantified value on the differences. Galaxies have smaller values, stars have more, planets get more, life forms a great deal more.
Right.
There's more energy per unit mass, more energy per unit mass flowing through your body per unit time than there is flowing through the sun.
Yes, I remember
this. About 1,000 times more energy per unit mass per unit time. And throwing through your brain is upwards of nearly 1,000,000 times more energy per unit mass. So it's a per capita measure than flowing through the sun.
That was, I thought, an excellent point in your book. I remember that vividly, and the scale going up to your brain, and then it becomes almost staggering that the human brain, which is not that big, but it uses this disproportionate amount of energy if you take that into consideration. So thank you for setting the stage there. I'd like to run through, and unfortunately we're running through your epochs. You've got, is it 7 epochs in the universe, and this is done so beautifully in the book that I think in the books, I guess, taken together, that people will be well rewarded to read them. Start with the beginning, with the particle epoch. You make some very good arguments, if I recall, about the different models of the universe. You went through these 3 models. Would you start us with that?
Well, my favorite model, philosophically, as an idea, is an oscillating universe. One that has no beginning and has no end. It just always has been oscillating. Currently it's expanding, and then it will come back and bounce into another. And it avoids any need for a big bang or an ultimate end. However, there's not a shred of evidence for that model. So I have to kind of put that in my back pocket and hope that maybe someday I'll observe something that might bolster it. But right now, the leading model is one that has a beginning and probably has no end. It's the Big Bang model. A lot of the data seem to be that we acquire telescopes and with spacecraft pointing increasingly so toward a notion, toward an idea that the universe began about 14 billion years ago in a very hot and very dense state. And then once it did begin, for whatever reason, we're not going there tonight.
Not inflation, no resist.
Well, it's not science yet, I think.
Yeah,
and it may never be part of the fabric of science to examine what is the origin of the origin. But for whatever reason, it did go bang, not as an explosion, but as an expansion. And we're along for the ride.
Yeah.
And the universe evolves, it changes, it's dynamic, it's not static. The steady state model, which was popular in Europe in the mid-20th century, is now put to bed pretty much.
Which some very prominent
scientists
and
they were the
promoted
ones,
at the time.
Out of derision, gave the name the Big Bang.
Right. May I ask you, what would be the best evidence for the oscillating universe? You remind me of Paul Steinhardt and Neil Turok, a book on that, but I don't know if they gave up in the end. But they worked on inflation, for example, and then they retreated and said, this isn't working, the oscillating. But what would be the evidence that you would accept that would tell you?
If the universe were slowing its rate of expansion outwards, which is what we thought we were going to find 10, 12 years ago. That is, if the universe was decelerating. But the data are, head-scratchingly, showing that the universe is continuing to accelerate outwards. And so I look upon that as unfortunate for those of us who would like the universe to eventually come back and oscillate. But on the fortunate side, look at the positive side of the accelerating universe, that suggests that there will be a rise and continued rise in complexity forevermore. And the universe will never come back to a point much like that from which it began. The rise of complexity and the expansion outward will apparently continue until infinite time. As hard as it is to imagine.
That is hard, isn't it? It really is, and counterintuitive for sure.
So.
And very hard to get our heads around something like that as well. But in any case, well, you gave us no comfort there. But in any case, I'm leaving the particle epoch behind here really quickly. Yes, right. But I'd like to dwell on the galaxy epoch a little bit. You brought out several things there, but one of the most interesting things about your view of that is that people really don't understand the emergence of galaxies very well. Is that still true?
Yes. It's probably the origin of galaxies is probably one of the 2 or 3 great missing links in this entire story. Origin of life and origin of intelligence might be others. But the origin of galaxies, which must have occurred all long ago because they're all old, there are no young galaxies, nor are there any dead galaxies that we know of. They must have all formed in the earliest universe, and that means they formed far away in space but long ago in time. And we can't see them very well. They're dim and they're dirty and they're dusty and they're far away. And so we like to say at the Harvard Observatory that galaxy research is probably 50 years behind stellar research. Stellar research really came into its own in the middle part of the 20th century. We're just catching up now among the galaxy research efforts. But every single day, the lunches I go to, the seminars I go to at the Harvard Observatory, where there are 180 PhD astrophysicists all assembled there, contentiously talking about this stuff behind closed doors. Most of that work now that's so exciting is on galaxies, along with exoplanets and others. But we're trying to understand, by bringing home more data from the earliest frontiers of the universe, how those baby galaxies became mature galaxies, how those baby galaxies emerged. How those first structures brought together enough atoms to make a galaxy. You need 10 to the 68 atoms to make a galaxy. That's a lot of atoms. You cannot do that by chance and chance alone. You cannot build a single galaxy in the age of the universe by chance and chance alone. Yet there are, we estimate, about 10 to the 11 or 100 billion such galaxies. Again, it's chance and necessity. There must have been a mixture in the early universe, the same as there is now. Whereas there were elements of chance that brought atoms together, but then the laws of physics also were involved with chance to assemble and to bolster the development of these early galaxies. And that's what we're struggling now with telescopes like Hubble and its successor called Webb telescope, and the Spitzer telescope on orbit, and the Chandelier telescope, to really see. We'd love to see a baby galaxy. We're not sure if we've ever seen a proto-galaxy yet, because we don't have a machine that we have built as human beings that can see well enough to those earliest epochs in the universe, where those galaxies had to have formed. We will get there.
Do you have a pet theory yet about the formation of galaxies? We hear about seeding, you know, obviously from
the hard thing about galaxy origins is that somehow, some way, the notion of dark matter comes into play. It appears from a variety of circumstantial evidence, nothing direct, but lots and lots of relatively strong circumstantial. Oh, it sounds like an oxymoron. I have a strong circumstantial piece of evidence that the universe has a lot of dark matter contained within it. In fact, the dark matter outstrips ordinary normal matter, that we call baryonic matter, by a factor of 5 or 6. And so not knowing what this dark matter is and how the dark matter actually interacted in the early universe, I don't have a favorite model because I'd like to hang my hat again as an experimentalist or an observationalist on what I'm finding observationally. And yet we're struggling to detect the dark matter. We can only infer it. So until we know more about the dark matter, or until we eliminate the need for dark matter by changing the law of gravity. You can futz around with the law of gravity, and instead of it being a 1 over the distance squared exactly, make it 1 over the distance to the 1.9 power or to the 2.1 power. You can start altering and making messy Newton's laws or Einstein's laws. But by altering the law of gravity, you can actually do away with dark matter. So not too many people are going there yet because there's something elegant and beautiful about Newton and now Einstein's laws. But somebody's going to take the next step beyond Einstein, just as Newton took the next step beyond Aristotle and then Einstein bettered Newton. Somebody's going to better Einstein.
But you think that's a possibility? No, you think that that's a possibility right there.
Yeah, it's definitely a possibility.
Tweaking that a bit, adjusting that a bit.
So unless we know more about the dark matter or how gravity operated slightly differently in the early universe, there's really no favorite model that I have.
Okay, so people are scratching their heads behind those closed doors when
very
they're
much a puzzle.
But I think we're not in the general public, the non-professionals, we're not so aware that people are bewildered really by the origin of galaxies.
In fact, normally we would prosecute science by a mixture of theory and experiment, ideas that need to be tested. There's a third element that's now coming into play, and it's very heavily on display at the Harvard Observatory in advanced seminars, and that's computer simulations. People will build computer codes that are very, very complicated, guessing how the galaxies might have come together. And then as the computer simulations run, they look like animations. Then they go out in the sky and say, well, does it look like that? Say, well, no, it doesn't look like that. Say, twist something else, twist another few knobs in the computer simulation, just trying to match by brute force what the computer simulation is showing and what's seen on the sky. Because the fundamental first principles are not there yet. The origins of galaxies. It's the greatest nut to crack.
But
whoever figures that out will go to Stockholm, all expenses paid.
Exactly. Very quickly and stuff. Another really interesting thing in the galaxy epoch that you brought up was radiant galaxies. I'm sorry, not radiant galaxies.
I was going to say, I haven't heard of that either.
Right. It's a new one, okay? It's a new one. Active galaxies, which are not radiant. Excuse me. Yes.
The dark galaxies.
Yeah, the dark galaxies. With so much energy.
Well, galaxies, you know, it's like pebbles at the seashore. There are a lot more pebbles than there are big boulders, and there are a lot more big boulders than there are gigantic rocks. There's a power law among the various things you see at the seashore. The big boulders are few and far between. The grains of sand are everywhere. There's a power law among the galaxies we're finding as well. The most common type of galaxy is the dwarf galaxy. Just 20 years ago, we dismissed dwarf galaxies. It's just debris left over. They're probably the building blocks of the galaxies. They're probably where the galaxies came from in many ways. We have no direct proof of that yet. But they're the galaxies that seem to be heavily embedded with dark material, dark matter, and very little radiance, if you want to call it, very little luminosity. So if you take, to get technical, the luminosity to mass ratio, it's very, very dark and very, very dim. In fact, some of them are just now in our local environments around the Milky Way being found because we had previously overlooked them. They're so dim.
Right. Is this analogous to the dwarf stars and the stars that have never
Very much so. There are many more dwarf stars.
Really.
There are many more dwarf stars than there are piddling stars like the Sun.
Right.
And there are many more stellar objects like the Sun than there are gigantic stars. So it follows the same power law distribution.
Right. The interesting thing was that you mentioned these have tremendous energy. They're giving off some huge amount of energy, which would be sort
of the active galactic nuclei. If they have a supermassive black hole suspected to be in their hearts,
so they do have
those are the ones that give a great deal of energy.
Okay.
Yeah.
Okay. I won't then dwell on that too much. I'll just run along because people have heard of black holes, and that's a whole subject all by itself, but except to say that you do accept that, or astrophysicists accept that it seems that black holes are at the center of galaxies.
Just last week I had a long conversation with an Australian scientist at lunch, and he just put down his glasses and he looked at me and he said, "What's the story? Do black holes exist or not? What do you really think in your heart?"
What do you really think?
We had about a 2-hour conversation. It wasn't simple. It wasn't a case where, obviously they exist, and we went on to another subject.
Right.
Well, some of us and he knew by pitching the question to me that I have an open mind about this.
Yeah. I know you have an open mind about it.
We haven't proven that black holes exist. There could be very strange objects somewhere between, let's say, white dwarfs or neutron stars and black holes. They've even been given a name, quark stars. Stars just made of quarks, which are the very fundamental building blocks of material, but which are not as bizarre, as truly bizarre as black holes. So I think that I have an open mind on this. It's going to be a long time before we can prove. It's hard to prove something. It's the same as Sir Karl Popper told us long ago. It's impossible to prove a theory is correct. You can only prove a theory is wrong. In many ways, if you have an idea like black holes, as exotic an idea as black holes, it's hard to prove that idea is so robust that they definitely exist. There's something strange going on, very bizarre, very unearthly at the centers of galaxies. But whether it's a real black hole, as Einstein might have taught us, I don't know. I have an open mind.
That's very interesting. That's.
But I think I'm in the minority on that.
Okay. Well, I was going to say, Stephen Hawking's already evaporating them. There's
not a shred of evidence to support that idea. That's the one conversation I had with him over the years was his Hawking radiation. And as an observationalist, I said to him many times, it's hard to have a conversation with Dr. Hawking, but my point was that I don't see the evidence. I have observed these objects repeatedly, looking for what he has said, and I don't see the evidence.
Right. I thought at one point he sort of retracted it. I mean, it was almost trivial because the rate of the evaporation would just be a little strange. But in any case, so we don't really know black holes, whatever they are. They're really a lot of uncertainty. Well, you're talking with other people who are uncertain as well. But it's important for the public to know that there is a lot of uncertainty and there's no way to confirm something until you find
But there is no question at the centers of galaxies
have something,
and at a few other locations within our galaxies, such as an object called Cygnus X1, that something very bizarre is going on, akin to a black hole.
All right. So then I'd like to go on to the stars here. And one of the there are a couple of special things in there, and one is the interstellar clouds, which you do a bang-up job of describing, because people don't talk about magnetism very much for reasons I don't understand. But would you tell us about the interstellar, so stars form, and then we skip to the interstellar.
When you look at the nighttime sky, you see lots of stars, and people kind of get the impression that that's all there is. What you see is what you get. But in fact, there's virtually an equal amount of material in the darkness among the stars. It's not dark matter. It's actual matter that we can find. It's atoms. It's mostly hydrogen. And we can sense it only with radio telescopes, and in a few cases with infrared telescopes. But you have to look in the darkness with devices at longer wavelengths, we say, in order to sense these regions called interstellar clouds, because they're so very cold. But much of the material out of which stars come and much of the material out of which stars, expel their material back out into the is the interstellar material, interstellar matter. And so it's very, very thinly distributed. In fact, it's orders of magnitude, easily 1 million times thinner in interstellar space, in and amongst the stars, than the best vacuum we can achieve in the physics department.
You brought that up.
So it's not a true vacuum. There is stuff we can detect there, and we can detect it routinely with a radio telescope. That was my research specialty. That was what I did my doctoral thesis on, interstellar processes, because that's where, again, the stars form.
Yeah.
And if you were interested, as we were in the 70s and 80s, in understanding how stars form, you could look in these darkened regions forever with an optical telescope, and you never see anything, because there's nothing to see.
Right.
These dark clouds are dark.
Yeah.
They're literally dark to our eyes. You have to sense them, and to sense the small amounts of heat and energy with radio and infrared telescopes.
So it was really the development of radio telescopes and presumably in the future other advanced technology that will open our eyes, so to speak, to what's out there.
I think that's why we're living in a golden age of astrophysics now more than anything else. So we've opened up the entire electromagnetic spectrum. We're not just looking at the universe in the optical domain. We're looking at it at longer wavelengths, radio and infrared. We're looking at it at shorter wavelengths, ultraviolet, X-rays, even gamma rays. We're sensing in a single generation, not the generation of my children, not the generation of my parents, but our generation who's now working this, the entire electromagnetic spectrum. And we're seeing just wondrous things at all these various wavelengths.
Do you expect, speaking of that, wavelengths and stuff, do you think there is anything else that they haven't discovered, something new
it's
out
hard to imagine there be anything beyond gamma rays, because we're already talking about wavelengths that are on the order of size and scale of nuclei. So there's kind of a fundamental the way which matter is built, upper end, I think, there. But the other end, which is, it's called very long wavelength radio frequency physics, or VLF, very low frequencies. The military is very interested in that. So there's a lot of effort being done there at longer wavelengths, wavelengths that are as long as mountains, wavelengths that are as long as continents. They're interested because those kind of waves penetrate water.
Right.
Whoever makes the oceans transparent will have a tremendous strategic advantage. But we better not go further in that point.
Well, we're not going to deal with that crowd anyway. We're not dealing with that crowd.
But there may not be a boundary
right,
there.
I see what you mean.
There may be very long wavelengths. And in particular, some people are now beginning to build for astronomy in the outback of Australia, in particular, and in South Africa, large arrays that might be able to see longer wavelength radiation that's coming from the early universe.
Yes. So that's what I mean. You would have a technology that would take you to this, and then you discover
astronomy is very much a data-driven subject.
Right.
And a question was asked to me the other day in Washington, why is it that we are making these leaps forward? It's because we're gaining better and better resolution with more and more sophisticated equipment. The history of astronomy shows that advances have been made in astronomy and astrophysics probably at the rate at which humans have built better machines and seen things more clearly. They've increased the clarity of view and resolution on the sky. And hopefully with the next generation of devices in orbit in particular, but also from the ground now as well, we'll see things another factor of 10 more clearly and take another leap forward. But it's very much a subject that's data-driven.
Right. And speaking of data, before we depart from that, is that the ability to take in huge quantities of
like
data.
Like drinking from a fire hose.
Exactly. Do you see that as changing the way you're doing your science today? Because you can go back and look at all this data.
The younger people these days are very good at handling enormous amounts of data and visualizing things in patterns. That's something that even I have trouble with because I wasn't just trained to do that. But there's a lot of emphasis now on informatics and pattern recognition and dealing with big data. Some people are even calling themselves big data scientists.
Well, there's a whole field now.
And it's not just in astronomy, it's in biology as well. Though many biologists, and neurobiologists in particular, are coming to the astronomers because they feel, I think in many ways in the biomedical community, with their imaging desires, that we have a jump on the action here because we're imaging the sky. But everybody's working in the same way to move toward acquisition of tremendous databases.
Yeah, right.
Yeah.
And it's just changing the way I'm
really
sure
is.
that
It
you're
really
looking
is.
at things.
Yeah, yeah.
Back to stars for a moment.
All right.
Among the sexiest stars, I'd
Sexiest
vote,
stars? I
say,
think stars are boring.
neutron star.
Yeah.
Come on, neutron stars. Do you have a candidate that you would tell us that you think is a star that doesn't put you to sleep or something like that?
Well, see, I think neutron stars are kind of boring because they are dead stars. They're not stars. We call them stars, like
Yes,
we call white
I
dwarf
understand.
stars. They're not stars. There's no fusion going on. They're just dead remnants
Right.
of formerly robust stars. And in particular, neutron stars, if we've got a handle on them, and we're still grasping that, are probably just giant balls, but no bigger than the city of Cambridge, of carbon.
Yeah.
It's just, and so in many ways, that remnant of a former star that had become reasonably complex has reverted to something that's relatively simple. If an object like a neutron star is just a ball of carbon, I don't need much information to describe that object, nor is there much energy flowing through that object per unit mass, per unit time. So in many ways, I think, although of course I'm being somewhat facetious, neutron stars aren't interesting to me because they're not demonstrating a great deal of complexity. They were once the heart and soul, I guess, of a central region of a star that was considerably, moderately complex. But now that they're no longer a star, they're dead. They're on their way to the graveyard. They're on their way to greater disorder. They're on their way, as supernova would, of breaking down their material and obeying the second law and spilling their materials outward into space. They're dying.
Okay.
I'm not interested in death.
Okay.
I'm interested in
what's coming
how
about.
things
Okay.
grow in complexity.
Okay.
And how they maintain their structural and functional capabilities.
I'd like to skip over planets in that case.
Good.
Okay, good.
Yeah.
Let's go to the chemical
Life.
epoch. Yes, and because that is particularly interesting, I'm not sure, again, whether people are aware that people in biochemistry and stuff say life is chemistry over and over again.
Yeah.
Tell us about this. You made a gorgeous case of this.
Yeah. Actually, I wish I had been a biochemist in many ways, because I think the advances being made in the biomedical community now is equally impressive.
It's really exciting.
As those being made in astrophysics. Though I was also at lunch at MIT a while ago, sitting next to a Nobel Prize-winning biologist who also admitted to me after a few drinks that he wished he had been an astrophysicist.
Well, there you are.
So maybe the grass is always greener in the other yard. But biochemistry is fascinating because it enables us to begin to understand how the rise in complexity didn't cross a line from what's not alive to what's alive, but just in a matter of degree ramped up its complexity to become aware of itself eventually. I doubt if a star or a galaxy is aware of itself, but we seem to be aware of ourselves. But life, because it is more complex, anything alive in my backyard appears to be more complex than anything on the sky. Is hard to understand.
Well,
even hard to
big
define.
Things, right?
Most biologists do not have a definition of life.
It's
Every
true.
physicist I know has a definition for matter. I can go anywhere in the world and ask any physicist, no matter where they've been trained, no matter where they live, no matter what their personal persuasion is, what is matter? And they all say anything has mass and takes up space. But if I have a room full of 12 biologists and ask them what's life, I come out with 12 answers. It's quite
very
one of which,
difficult.
of course, is I know it when I see it, which can't be a definition for life because that's the Supreme Court's definition for pornography. So I've tried to develop, over the course of my studies of cosmic evolution, a definition for life, which is very long-winded, and people will criticize it because it's long-winded. I'll tell you what it is in a minute. But at least I have a definition, but it's a thermodynamicist definition.
Okay, that sounds
good. And it is as follows, that life is a coherent, open, space-time structure kept far from thermodynamic equilibrium by a flow of energy through it, a carbon-based system operating in a water-based medium with higher forms metabolizing oxygen.
Okay.
It's
right.
You know, it's a long word, but at least I have a definition.
Yes, that's right.
It's a
would you
working
insist
definition.
on the carbon base? There are people that would say
that's life as we know it.
Okay.
That's
all
life
right.
as we know
there
it.
There may be some other options, but
some students in my class have written fabulous papers on life as we might not know it. For example, silicon-based life operating in ammonia-based medium. It's all possible. But the only life we know, the only life they study at MGH or at Harvard Med, is based on carbon.
Right. Right. Okay. And then you also take up the question whether life is inevitable, given your evolutionary scheme there, and that's a hard question, actually. Is it, in your mind, inevitable? Or?
It seems to be, as the universe is expanding, and probably only because the universe is expanding as a prime mover, that complexity is rising in these islands of growing order. But it doesn't necessarily mean that those increased complex islands will become alive as we know it. The question is, as matter moves from simplicity to complexity, does it inevitably come alive? Or is it simply a natural process? We seem to be part of this story in a natural way, but it doesn't necessarily follow that as systems become increasingly complex, that they inevitably become alive, conscious, able to reflect upon themselves.
Certainly not conscious, right, yeah.
Galaxies, stars, other systems that are clearly not alive could become increasingly complex in the far future. But evolution is not a predictive science. It's not like Newtonian dynamics, where you throw a baseball, and if you know all the spin of the ball, the air resistance, the mass of the ball, the velocity, you can predict it exactly where it's going to hit the catcher's mitt.
Good point.
It's not true in evolution. Evolution is not, so I hesitate going out into the future as much. But that's why we were puzzling in Washington recently, asking, as Fermi asked long ago, if life is so inevitable elsewhere, and the universe is populated with life forms, then where are they? Why don't we have some evidence of it? There's no unambiguous evidence whatsoever that there's anybody else out there yet from an observational or experimental point of view.
What's your view? Would you have the
It's
optimistic
hard to believe.
view?
Yeah. Like I used to say to Sagan, I have a realistic view. He had an optimistic view. He saw life in his mind everywhere. And I had enormous respect for Carl Sagan. But I would often say, we're never going to know sitting around a table just talking about it. We've got to go out there and do an experiment. In particular, use a radio telescope, ideally, to try to eavesdrop on other civilizations that might be there. It's hard to believe, if you want to, believe.
A lot of planets out there.
Hard to imagine that of the 100 billion stars in our galaxy alone, and maybe billion habitable planets, that life has not arisen. But it's also easy to understand how many of those life forms might have not moved beyond creepy crawly status to intelligence. Just looking at the fossil record on the Earth alone, single cellular life forms remain for billions of years without starting to develop a central nervous system and becoming intelligent.
Exactly, and a lot of it looks entirely accidental, but the potential exists in any case.
Exists, yeah.
You brought up, if I remember, something that I always personally find missing in these things, and that is time, that these things require time. And so in terms of life developing, it's very clear in our fossil record it was very slow, and you had to have certain conditions, some of them catastrophic, before you could really move in evolution. Do you think that that is a big factor, that having large amounts of time? What I'm trying to say is that many people looking at life say a half a cup of this, a teaspoon of that, put it in a vat, add a little electricity, shake well, and tomorrow you'll get some amino acids.
Yeah. You can actually, in your bathtub, do what you just said.
Yes.
I was involved peripherally in the film that Julia Child made for WGBH long ago, where she took the building blocks of life and put it in her cooking machine and zapped it, and she got the answer. She couldn't pronounce any of the terms properly, the biochemical terms, but she got the correct answer. She got the amino acids. Just as I could do, and I've done once, but I don't recommend it because it makes a hell of a mess. Take the building blocks of life and zap it in your bath, and you get the correct amino acids. But nobody is yet going beyond that.
Exactly.
There's no life crawling out of the test tube or out of the bathtub. There's a tremendous, I don't want to say there's a difference, although there's a dividing line between what's not living and what's living. I think it's a degree of complexity that must, a threshold of emergence must be bettered in order for something to move itself onto the path that we would call living.
Okay, and maybe it takes all the conditions that have to be right, presumably pretty right and stuff.
The analogy I used in Washington recently was that our entire galaxy is like a huge chandelier, the biggest chandelier you could ever imagine, where there would be a chandelier of 1 billion bulbs. And as each bulb, which represents a star having a habitable planet orbiting around it, experiences evolution, the bulb gets screwed in and the bulb lights. Mm-hmm. But at any given time in the history of the galaxy, there may be very few bulbs. In fact, there might only be one bulb at any given time lit. Mm-hmm. Right now, my imaginary galaxy has us way out at the edge of in the suburbs of the galaxy as a rather dim and dirty bulb. And we're hanging on, kind of, hoping that light stays lit. But at any given time, although all the bulbs in the chandelier will eventually light over the history of the universe, at any one time, there may be very few bulbs, indeed only one. So there's nobody necessarily to talk to at any given time.
Well, there's some huge different distances involved as well. But on the other hand, it wasn't that long ago, as I remember vividly, that when people started looking for planets, they were considered completely crazy. Yes. The next thing you know, we have hundreds of planets. Yes. And then it goes like this, it's accelerating, so that we may change in 20 years if we survive.
So now we have maybe 1,000 habitable planets. Just in the last decade or so, and a half. But that makes my puzzle even deeper. Namely, if we now have experimental evidence that there are thousands of habitable planets, probably more like billions of habitable planets, then why don't we hear a signal? Why don't we have some sort of a message? Why haven't we eavesdropped on some other advanced civilization?
Do you think they'd want to talk to us?
Well, I don't know. Would you want to talk to an ant?
No, it's for one thing the huge distances.
Of course.
We would all love to.
Time and distance are an essential part of this story.
Right.
But go ahead. Yeah.
I want to just skip again, for lack of time. Why did you include a cultural epoch in the evolution of?
Well, if you ask social anthropologists, and I've asked a lot of them, I enjoy having lunch with social anthropologists. What is culture? Mm-hmm. Many of them will actually suggest, without even a hint from me, that culture is the quest by society to control energy. Mm-hmm. And so again, you come back to the same kind of nuts and bolts of my story, that stars have a flow of energy, galaxies, planets, life forms, societies. Culture itself, in form of a civilization, has a certain amount of energy flow per unit time, per unit mass, and that has increased with time. For example, since the birth of agriculture, just 10,000 years ago. Even before that, hunter-gatherers used a certain amount of energy, agriculturists use more, industrialists use more, technologists, as we might call ourselves. The per capita use of energy is rising just as the energy rate flowing through all these other complex systems. Yeah. And there's no reason to not include culture in this grander scheme of cosmic evolution, so that it becomes cosmic evolution, a mixture of physical evolution among stars, galaxies, biological evolution of life, and cultural evolution of advanced, truly sentient life forms.
It's a very interesting point, because I don't know if anybody else has ever thought to treat culture in quite that way, as a natural outcome of an evolutionary process.
Well, I scare a lot of anthropologists by saying, well, let's do the numbers now with thermodynamics. And the thermodynamics treatment of culture is a little odd, but that's my point. You can treat it on the same page. You can examine everything you see out the window over the entire history of the universe in the same manner, the same uniform, consistent manner. You're not treating this separately or specially from another. You're treating everything on the same tabletop. It's a level playing field for everything I see out my window.
Right. I hope that people will be encouraged to read these books. Well, either one of there's one that's more accessible than the other, but I think it will change their perspectives very considerably. Very rich reading.
Thank you.
And thank you for doing that job for us. I think you said it took 19 years to write that?
Well, the simpler book that would appeal to most people, I think, because it's more readable, took me 6 weeks to write, because it was all in my head.
It was that one?
Then the mathematization of the simpler book which is a very complex book, but it's the same story. That took me 19 years of manipulating to write.
Well, we appreciate it very much. You've
Same books,
been such a service to humanity with this. Thank you very much. And I will now turn you over to let people ask you some questions.
All right.
Okay, thank you very much. I'm going to...
I wanted to ask you a question that relates to cosmology, although that's probably the most speculative of all the disciplines that were discussed this evening. But given that speculation, you said you made an interesting point about the recent observations showing that the universe is expanding at an accelerating rate would seem to be counter to the possibility of an oscillating model, but on the other hand, could allow for a universe in which complexity could increase without end.
Right.
However, at least one interpretation of this acceleration of expansion, which would be based on some repulsive force that I guess some call dark energy,
Yes.
is that eventually not only do all the other galaxies disappear from our horizon, but that at some point a big rip occurs, which would seem to break all matter down to its subatomic components and be the opposite of complexity. And I was just wondering if you've reconciled that model with...
Well, ultimately, I do think that thermodynamics will win out. Thermodynamics will trump gravity. Thermodynamics and the movement toward greater disorder, second law of thermodynamics is the most fundamental law in all of physics. It's the last law that the physicists are willing to give up. So I think everything eventually will break down in some way and become once again simple. But we're talking so far into the future, and we're talking so speculatively.
Right.
I really don't necessarily want to go there because, again, I'm that observationalist. I'm that experimentalist. Much of physics these days, unlike the physics that I was trained to know and love in the 70s and 80s, is not bolstered as much these days by experimental and observational data. And many of these ideas as to what the universe might be going to do in the far, far future, or what evolution is going to, where it's going to take us, it's just entirely speculative. And the ideas are not even bolstered with not just a lack of testable data, but testable in principle.
Right.
Physics we need to come back a little bit, I think. We need to have good, solid ideas that have a degree of speculation, but the job of the greatest theorists in the history of science is that they also propose tests that can be made of their ideas, that can disprove, or you're never going to prove an idea right again, you can disprove it. But that's how science operates, and I think right now we have such a plethora of speculative ideas. And this RIP idea, I think, is one of those. Multiple universes is another.
Yes.
String theory is yet another. Nth order dimensions. It goes on and on and on. Where did these ideas all come from? They're wonderful ideas, but they've got to be tested in some way before they come into the fabric of what we call physics. Unless physics itself is evolving in ways that they will say to me, you're showing your age, Jason. Which is probably true. Your points are well taken, though.
But you asked a rhetorical question, where are these ideas coming from? I guess you could cop out and say they come from the complexity of the human mind.
Yeah.
So basically, I'm going to ask this question in a couple of different ways. What drives the succession of epochs? In other words, is there a succession of epochs?
Okay.
What drives that succession? Is it possible that there is something in the arrow of time that makes it want to go, the arrow of complexity, really, in your conversation, you, I think, prefer that term. I could also talk about entropy too, but I hear you that you don't want to hear me do that. The complexity, the arrow of time wants to go faster and faster and faster, and that these epochs are generated as time's way of moving faster and faster and faster, generating complexity faster and faster, and generating more and more complexity. That's your perspective, right?
More or less.
Why does that happen?
Because the universe is expanding. I do think the reason for what you're driving at is, you're asking what is the prime mover of all this. And I think in an expanding universe, which did begin to expand for whatever reason that I don't know, the prime mover is that in an expanding universe, the flow of energy will continuously increase. It's not an increase in energy specifically, but it's a flow of what we call thermodynamically free energy. It's freely available for use in constructing systems. The earlier universe, everything was thermodynamically equilibrated. There was no real flow of free energy capable of building things. Indeed, the early universe was characterized by simplicity. But then as the universe cooled and thinned, simply and solely because the universe is expanding, it's cooling and it's thinning, inevitably so.
And you can extrapolate from that theory, which works best when you're looking at the universal structure as a whole, to the generation of biology here on this planet. That's what drives, at some level, natural selection.
An argument can be made for that, and I'm making that in some part. I'm suggesting that natural selection operates in part because of the flow of energy through open thermodynamic systems which are living. Part of natural selection is due to the flow of energy.
Right.
Naturally, some other parts are due to information contained within the genes.
But on this level of talking about what's driving the succession of epochs,
right,
what is it? Is the thing that is driving the succession to biology, to culture, the same thing that was driving the succession from galaxies to star systems and so on?
I'm suggesting to you that yes, the answer is the same flow of energy, but flow of energy per unit mass, per unit time, associated with these islands of complexity. It's the same process operating, whether you're a star and you're benefiting from a flow of energy per unit mass, or whether you're a human being, or whether you're a society experiencing physical, biological, or cultural evolution. It's the same process.
And it all
At least that's the hypothesis.
And it all traces back to the expansion of the universe.
Well, I do think the flow of energy, which is absolutely central to this idea, to this working hypothesis, does date back. It dates back actually to about 380,000 years after the Big Bang, when the universe decoupled and had a symmetry break from a universe that was full of simplicity to one in which atoms could then begin to come together somehow, some way, to build the galaxies, the first galaxies. And once that begins to occur, you build your galaxies, which are environments suitable for the eventual spawning of stars. The stars with it come as a byproduct planets. On some of those planets, maybe only one, I doubt it, perhaps many more, habitable zones are sufficient to give rise eventually to life. Life evolves through the same process of energy flow, in part to become more intelligent, and then to reflect back upon this whole story, and to enable us as a sentient species to tell this story. That's the sad part about it. If we ever were alone and don't survive, this great experiment called life would end. In which case, the stars in the galaxies would continue shining and twirling, but nobody would know anything about it. We have emerged on this one planet, at least, and it's hard for me to believe that others aren't there, out there as well, to tell this story. In many ways, this should be, I suppose, I could claim it is, the greatest story that ever might be told. The cosmic evolutionary story from Big Bang to humankind, in fact, from Big Bang to humankind and beyond. But I don't know what that beyond is because, again, evolution is not a predictive science, and I'm not going to speculate about it. But your points are very, very well taken. Yes?
Life seems to be unique in that it, instead of increasing entropy, it concentrates energy and is opposite to the rest of the universe, which seems to be cooling off. That seems to me to be very special.
All open complex systems share that same peculiarity, though. Stars, planets, life, society. We all have a flow of energy into our system. Let's take your body. You eat a certain amount of food. You eat on average about 2,800 kilocalories per day. and then you have a certain flow of waste, which is entropy, out into the environment. You're contributing, so am I, to the increase in entropy of the universe. But so is a star, so is a galaxy, so is a planet. I mean, that's the problem we're having now. As we ramp up in the use of energy as a civilization, we are creating a lot of waste. We're creating a lot of disorder in our surrounding environment. But that is the natural way in which the second law of thermodynamics governs each of these systems. Life is no different from any of these systems I've been describing. It takes in a certain amount of energy. It utilizes it to build structure and to exercise function. The energy is acquired, the energy is stored, the energy is expressed. But after the function has occurred, out goes the waste, out goes the products, out goes the entropy. So all these systems, complex systems, are temporary islands of decreased entropy, sitting in an environment of increased entropy. In fact, you want to do the calculation, as I always do in some of these journal articles and books that I write, to make certain that the sum of both the system, let's say your body and the environment, or a star and its environment, or a black hole candidate and its environment, that although the entropy is decreasing within the system per se, that it better be increasing. The entropy better be increasing when you consider the system and its environment. Otherwise, you're in violation of the second law. And boy, I don't want to go there. The second law is the most cherished law in all of physics.
But life has the potential of increasing exponentially, so that
and we're seeing the data. The data are suggesting that as you move from simple life, unicells, through multicells, or prokaryotic systems to eukaryotic, that it has risen exponentially. Yeah. So you're just telling me what the data are showing. And increasingly beyond life per se, clusters of life, clusters of society, of civilization. Take cities. I've been examining cities in great extent lately. 55% of all people live in cities, and within about 20 years, about nearly 80% of people are expected, according to the United Nations, to live in cities. The greatest human migration is underway now. 1 million people, on average, are flocking to the cities per week. It's a tremendous movement of people towards cities. And as a result, the energy rate per unit mass, per unit time, in cities is spiraling up. And spiraling up much more so than you individually, or me individually, because people are coming together, clustered together, just as the atoms cluster together in stars and galaxies.
If we're successful, though, we'll populate the universe.
Well, that's a heavy statement.
I said if we're successful.
That's a long time in the future.
Yes.
I'd rather not think that we take our earthly problems elsewhere in the universe with us. Yeah.